So in this question, we have a student must determine a non-zero change in momentum. And that non-zero just means it is not zero. It's like +5 or -6 or some other number. For a specific interval of time, a delta t. Which experiments could the students conduct? Select 2 answers. So if we want a change in momentum, the change in momentum must be an m delta v. We must have a change in velocity. So we drop a ball of known mass above a motion detector. So if we drop it, that means that the initial velocity will be 0. So we drop the ball above a motion detector. It falls down like so. And right before it reaches the motion detector, we record the velocity. All right, well, that will, since we know the final velocity and the initial velocity, we can find delta v. It looks like this will allow us to do it. Now, we should also know the mass, so we'll look for that to see if it's in any of the other choices. Drop a coffee filter. Now, a coffee filter is it's like a folded, dented piece of paper that's going to drop. And if we drop that, this coffee filter, it actually very quickly reaches terminal velocity. So even though there's a v0 equals 0 component, after we drop it, it's not going to fall very far at all, and it's going to have constant velocity. So we're actually not going to observe a change in velocity. There'll be this v, and there will be this final velocity. Oh, and this one said known mass, so we do know the mass and the change of velocity. So the coffee filter has a known mass, and record the terminal speed before it falls. So the motion detector, so what we have is initial velocity equal to 0 and a final velocity that will be the same velocity over a big chunk of time where there is a constant velocity. So we do know the mass of the filter, and we do know the change in velocity, and it wants it for a specific interval of time. So if this motion detector put out a position, so if we did the velocity time graph of this, it's going to increase like this and then do that, or be a little more curved like so. The velocity time graph in the first case is just going to be like this. So here's our time interval, delta t, there's our velocity. So there's a delta v over delta t. So on the face of it, choice B should also work. It's a known height. Record the terminal speed of the coffee filter as it falls. We know this terminal speed here. And so the question then becomes, what's the time interval? The time interval that there's a change in momentum would be this delta t, not the entire one. So B could be an answer, depending on how the other choices work out. So pull a block of known mass along a rough surface. It's rough, with a spring attached to the block at a constant speed for 5 seconds. Well, if we're looking for m delta v, the block has a known mass, and there's no change in velocity, the change in momentum we'll get will be 0. So C is definitely out. Give the block a known mass and initial velocity so it slides across a rough surface in front of a motion detector, slows down, and eventually stops. So here's our V and our T. And if it's a rough surface, it will do this over time. If the force that the thing is applying to it, the roughness of the surface, is the same as it's flying over that surface, the velocity will experience a constant acceleration and like that. And so when we look at the three choices, it looks like A and B and D are possible. The difference between A and B and D is that there is a constant continuous acceleration over the entire interval for D and A. It's only part of the interval for B. So for that reason, A and D are better answers, but B could be true if we define delta T differently. I would suggest that this is a kind of sloppy question on the AP's part because B is a legitimate answer, although A and D are more consistent with each other because the delta T is the entire interval being sampled.